Everything around you, the chair you're sitting on, the screen you're looking at, your own hands, is made of matter. And all of that matter is built from microscopic units called atoms. In the early 19th century, scientist John Dalton proposed that these atoms were the ultimate, irreducible building blocks of reality. He pictured them as solid, indivisible spheres, behaving like microscopic billiard balls that simply couldn't be broken down any further. That tidy concept hit a wall during routine electrolysis experiments. When Michael Faraday ran electrical currents through liquids, he noticed something strange: the undeniable presence of charged particles moving through the solution. This created a severe physical contradiction. If an atom is truly an unbreakable, electrically neutral marble, how is it capable of carrying or transferring an electrical charge? A completely solid sphere has no internal mechanism to make that happen. Faraday's observations proved the solid sphere model was incomplete. To figure out how physical reality actually works, scientists realized they had to crack that sphere open and search the invisible space inside. The first concrete proof of internal structure came from J.J. Thomson. He discovered a tiny, negatively charged particle called the electron, confirming atoms had smaller, moving pieces. Thomson proposed what became known as the plum pudding model. He theorized electrons were embedded within a uniform sphere of positive charge, like fruit scattered throughout a soft pudding. The layout of negative particles perfectly balanced the positive mass, maintaining overall electrical neutrality. But theoretical math is one thing, physical durability is another. If that positive charge was actually just a soft, uniform paste, it wouldn't offer any resistance to a high-speed, high-energy impact. Thomson balanced the equations of electrical charge, but his assumption about a soft structural layout left his model highly vulnerable to real-world physical testing. Ernest Rutherford put that physical structure to the test. He devised a daring new physical experiment. He fired a stream of heavy, fast-moving alpha particles directly at a microscopically thin gold foil. Based on Thomson's soft pudding model, Rutherford assumed the heavy alpha particles would tear straight through the gold atoms, barely slowing down. This diagram shows what actually occurred. While most alpha particles pass through, a tiny fraction hit something intensely hard, bouncing violently back. Rutherford concluded the atom is overwhelmingly empty space, with a microscopically tiny, incredibly dense positive core, the nucleus. This produced a planetary model, with electrons orbiting the dense central nucleus. There was just one massive problem according to classical physics. An orbiting, accelerating electron must radiate energy. As it bleeds energy, the electron should instantly spiral inward and crash into the positive center. Rutherford successfully mapped the physical core of matter, but his blueprint mathematically predicted that every atom in the universe should instantly collapse in on itself. To resolve this physical paradox, a Danish physicist named Niels Bohr proposed a radical new set of rules. This schematic visualizes Bohr's solution. Electrons do not spiral freely. They are firmly locked into discrete energy levels, labeled K, L, M, and N. They can only leap between levels by gaining or losing exact amounts of energy, preventing a crash. The outer architecture was finally stable, but the center was still missing mass. Later, James Chadwick discovered the neutron, a subatomic particle with zero electrical charge, but significant weight, which perfectly accounted for the remaining mass. This illustration shows the complete modern architecture: protons and neutrons locked in the center, surrounded by electrons in precise outer shells. The specific count of electrons in the outermost shell determines valency, its capacity to chemically bond and form compounds. Bohr and Chadwick established the strict architectural rules of the atom. In doing so, they revealed the precise mechanics that allow individual atoms to link together and build our physical reality. We identified different elements using their atomic number. This is a strict, unchanging count of the protons in a nucleus. Carbon always has 6 protons. Oxygen always has 8. But scientists eventually noticed an anomaly. Atoms of the exact same element, carrying the exact same number of protons, can sometimes have entirely different physical weights. These variations are called isotopes. They are atoms that share the identical number of protons, but pack a varying number of neutral neutrons in their core. Hydrogen, for example, always maintains one proton, but its core can hold 0, 1, or 2 neutrons. Tracking these extra neutrons proved highly practical. Understanding the precise behavior of isotopes gave engineers the leverage to actively manipulate these atomic structures. By isolating incredibly heavy, unstable isotopes of elements like uranium, we learned to harness atomic decay to fuel massive energy generation in nuclear power plants. In medicine, physicians utilize specific radioactive isotopes to map internal organs, track chemical reactions deep inside the body, and target specific cancer cells for destruction. We began by assuming matter was an unbreakable, solid sphere. By testing that assumption, finding the empty space, plotting the electron shells, and mapping the heavy nucleus, scientists extracted the rules of the invisible universe and gave us the tools to actively engineer the visible world.